first off, welcome. If this is your first time, I think I see a few new faces. I'm David Minsky, the Executive Director of the Data Institute. We have a really great speaker today. Before I introduce him, though, some brief announcements. We have our Machine Learning for Business certificate course starting, I believe, in October. All right, I got the month right. There it is, 21st. It's actually designed for people at the product manager level and understanding how businesses use machine learning effectively. What I'm really excited about is these two seminars right here. We have two new data ethics seminars coming up. One is soon, the 23rd, and then October 3rd as well. The first one we had was incredible, and also we have a few more seminars coming up, but no seminar next week, right? You have a break from seminar because all of the students will be in pitch week. So this is also a time where I would usually recruit. Hey, if you have a company and you want to have graduate interns, we don't recruit anymore. We have too many. The students are reading 150 pages of pitches this weekend to get ready for a week filled of listening to 5-minute talks by 70 different groups. So we're going to take a break from seminar for that reason. So I will see you the week after. I think I've done it. Did I miss anything, Andy? All right. So without further ado, though, I'd really like to introduce someone that I've gotten to meet over the last few years, which is Phil T, the co-founder and CEO of Moogsoft. And I obviously have a little bit of a crush on the talk he's talking about. It's around networks, and his perspective in particular is one from physics, which I doubly appreciate. So without further ado, let's welcome Phil.
Super, thank you. So are we going to cut over to that?
Wait. Oh, yeah, right.
Yeah. Yeah, we turn on that. There we are. Marvelous. Excellent. Well, thank you very much. And it's a superb fun to be invited to share a little bit of perspective on how in a real-world environment we use data science to try and solve problems for lots of companies. I'm going to molest you a little bit with what's important to Moogsoft, my employer and the company I started. But you'll notice that there's a couple of fairly odd logos next to my name because I'm a complete imposter. I sort of spread my time between this software company that I run and love, but we also at Moogsoft have a research function, which is a little unusual for a 230-person venture-backed company in Silicon Valley. And that kind of comes out of my first love, and probably the last words on my lips as I die and exit the earth will be, theoretical physics is really good fun. So I hang out with some folks down at Arizona State University at the Beyond Center for Fundamental Science. That's kind of cool. And the University of Sussex on the south coast of the UK in Brighton is where I spent 6 years of my life getting a couple of degrees and doing all that kind of fun stuff. And if you're ever in the UK, by the way, you can probably tell I'm British, right? If you're ever in the UK, Brighton's a fun place to go. Do go to the Market Diner after midnight. So the talk I'm going to give today is about unreasonable effectiveness of graph theory in actually network management. It's a pure commercial application of graph theory. Now, I don't know if anybody's ever heard the phrase unreasonable effectiveness of mathematics after Eugene Wigner, a Hungarian mathematician, physicist. And it's this kind of curious thing that I think in science, we don't think about enough, which is why it is that we're so damn good at working stuff out. It really makes no sense that we can use the human mind to really understand the physical world in which we live. And maybe that's why my email signature is the Heisenberg quote about we don't see nature itself, but nature exposed to our line of questioning. And to give you an idea of how unreasonably good, there's this thing here which, I don't know if anybody's heard of the anomalous magnetic moment of the electron, right? So this is kind of a wacky, crazy thing. If you look at an electron, it's got spin, except it's got a very strange type of spin. It sort of goes around twice for every one revolution of a real spinning thing. And even that's not exactly correct. There's a tiny, tiny, tiny correction because of the cloud of virtual particles that quantum field theory says must exist around a spinning electron. And if you do the calculation, which is reasonably hairy, throw away a few infinities, which makes mathematicians blush, but it's okay, it all works out in the end. You end up predicting this calculated value for the difference between 2 and what you measure in the lab. And it's accurate to within the thickness of a human hair compared to the distance from San Francisco to London. And you know, I do that journey quite a lot of times every year. So it's kind of incredible to think that you can get that close. It's a long way, and a human hair is pretty thin. So there's definitely this unreasonable effectiveness. And after all of that highfalutin fun stuff with quantum field theory and anomalous magnetic moments of the electron, let's talk about fault localization. And you know, the purpose of this talk is to try and convince you that one of the areas that's maybe less talked about in machine learning and data science, but we make sort of free abandon use of it in our business, is graph theory and network science. And it's unreasonably effective there. That's what I'm going to talk about, so I shan't go into that, but let me give you the background. A bit about me, I've kind of told you, I'm an old guy, I guess, compared to the average age of the people in this room. I've been building software companies for 30 years. I've built a couple of public ones, which is always nice to notch on your bedpost kind of thing. Couple of IPOs, a couple of trade sales, PhD in informatics. I publish actually across a wide range of areas, from pure informatics, network science, cancer. Seriously, it's a graph. And quantized spacetime, which is kind of fun. So what is this thing that is the commercial application, fault localization? So we have about 130 customers at Moogsoft, and they range across some of the biggest networks that you will come across. So American Airlines, Bank of New York, Ubisoft if you're a gamer. These are all people, they've got billions of dollars invested in computer infrastructure. And you know, what's the common thing about computing infrastructure? Anybody want to guess? Well, it doesn't work very well, right? It keeps failing, right? You know, you go onto your Netflix account to watch you know, the latest episode of Mindhunter or something, and the damn thing sits there spinning because something went wrong on an Amazon availability region or inside of Netflix. So there's this availability issue. And what people do to try and sort of get around that is they monitor their systems. We collect all kinds of things. We collect SNMP traps. Ever heard of that? We collect system messages out of syslog or application messages. We connect to other systems that are specifically monitoring sub-pieces of this. And the idea is, if we do our job right, we can work out from all of those notifications what is really going on inside of a customer's digital infrastructure and fix the problem before I get bored with the spinning Mindhunter icon and go and watch Endeavor on Amazon Prime, which, by the way, Endeavor's excellent, which is very good. So what you have there is this massive sort of data reduction problem. All of these events that are coming in, they're telling you stuff. Most of it's junk. How do I get to the stuff that I need to go in action? And that process loosely is called in the industry as fault localization, root cause analysis. There are a few other terms that people sort of bandy around. And it turns out that it is a data science problem today. And part of the reason why it's a data science problem is because the complexity and the scale of those infrastructures has gotten to the stage that it's difficult to do any other way. If you're interested, there's a couple of reviews by Steiner and Sethi that you can go look up. I'm sure these slides will get distributed. And it kind of covers the kind of the gamut of all the various different techniques. We're going to focus on a few. This is sort of a personal story, but the kind of the history of how all this works is kind of a fun one. About 30 years ago, I'm careful about how many years I say. About 30 years ago, I was living in Paris. I got sent there because I was captive by Air France to help them with managing their networks. And they had a very interesting problem at Air France. They were required to employ across the whole educational spectrum and the people with the smallest amount of education ended up operating their networks. That's kind of how it goes. And the issue was because of their relatively scant education, their command of the English language was somewhat limited, whereas all of the computers that they spent money on all spoke English. And so quite literally, they sat there with a sort of an English-French Larousse dictionary, translating disc en panne to disc failed, and it's like, oh, crike, we've got to go and do something. So I was involved in building a tool that basically translated error messages from IBM mainframes from English into French. And along the way, we accidentally invented this kind of console consolidation, and as soon as you get all the alerts in one place, there's kind of the first thing you ask is, which ones of these things do I need to look at? Which ones can I throw away? From there, we ended up really starting the chain of companies. I co-founded Micromuse, founded Riversoft, co-founded Moogsoft, and here we are. Moogsoft, if you're interested, again, I won't belabor the point too much. We're a super fun and groovy 230-person company that if you're thinking about earning a living in the software industry, please do kind of track me down. Because we have an awesome culture and it's a lot of fun. We tackle difficult problems. And also, you won't have to fully leave behind the wonder and the excitement of intellectual pursuit, because we fully fund a bunch of PhDs. We have postdocs on our payroll. We do active research. We do all kinds of fun stuff, and we file a lot of patents. Our product, I'm not going to really spend any time on this. Basically, across from left to right, remember I said all about the events, we bring it in. We use pretty much the entire smorgasbord of data science techniques. We get rid of noise using information theory. We're going to spend most of the interesting bit, hopefully, of this talk talking about that. And then we put that through a layer of unsupervised machine learning for clustering of alerts. And then we put it through a layer of supervised machine learning where we build models about causality and try and help customers identify the faults that they need to go and act upon. And then there's a bunch of other stuff that we do on top of that to automatically extract using some sort of basic sort of natural language theory, run books of what were the resolving steps and what did people do to fix the problems. So end to end, these are the 50 patents and the 16 or 17 papers that we published are all about the different algorithmic techniques that we apply there, and that's a bit boring, and that's also a bit boring. So because you don't want to hear about Moogsoft. So a lot of what we do, there's something of a common theme in Moogsoft that graphs, in a mathematical sense, tend to figure quite a lot in what we do. And graph theory is one of these things that I remember talking to one of our collaborators at Sussex, now Professor Istvan Kist. He wasn't a professor back in the day. Why don't you teach graph theory at the university? And he kind of looked at me and muttered something about maths departments being full of people who do analysis, and isn't that a pity? And and if only the world was more grown up, we would teach this to children. It's super important. So graph theory is kind of not necessarily always as familiar as it probably should be. I'm not sure, do you teach graph theory here, David, or?
Only through some network stuff.
Only through some network stuff. All you need to do is go and buy the Bolabas book. It's got everything in it you need to know. So just very, very, very quickly, a lightning course on graph theory. Really, all a graph is a set and a set of pairs of members of that set, right? And really what we're talking about is the set is the nodes, the points, and the pairs are the edges, the connections between 2 points in the graph. It's an incredibly intuitive concept. Everybody gets that, right? But the interesting thing about graphs is there's all sorts of interesting algebraic structure that you can build on top of this. There's lots of questions that you can ask about graphs when you model real-world problems as representations of entities and relationships between entities that are incredibly powerful. So, a couple of bits of terminology. You start to refer to things as undirected graphs if you don't put an arrow in the most naive sense on the link. So in other words, the edge between I and J is the same edge as between J and I. to sort of be more precise about it. We like to describe simple graphs. Most of the things that you do are a lot more straightforward, hence the name with simple graphs. And a simple graph is a graph where there's only one connection, one edge between two nodes, and there are no, I actually got into an argument in my Viva about this, and there are no self loops. The argument was whether it was correct to call it a loop. Or in other words, edges that start at the one node and end at the same node. Okay, so simple undirected graphs tend to be what we focus on, and unweighted means that we don't stick a measurement on the edge. Okay? One of the things that we get all kinds of excited about in network science and graph theory is the degree of a node. The degree of a node, typically in sort of network science world, you write K for degree. Graph theory, you see D used a lot. We'll use K. The degree of the node is nothing more than the number of edges that are incident on a particular node. Okay? The reason why people get all kinds of excited about the degree is possibly the most famous person in network science, a man called Barabasi. Anybody heard of Barabasi? Oh yeah, there you go. Lots of people know about Barabasi. Used a model of network evolution that he came up called preferential attachment to predict what the probability distribution is of node degree across real-world networks. So, in fact, this concept has been known forever. It's sometimes called in economics a Pareto distribution, the idea that there's a very small number of very rich people, and then there's a lot of us. So there's kind of Donald Trump, and then there's the rest of the world, right? And these sort of super hubs in wealth or super hubs in connectivity kind of fall off as a power law, which tells you lots of things about the underlying physical process. Barabasi predicted that, and it's kind of cool. So you can split graphs up. You can chop them into subgraphs, which is kind of fun, if that kind of thing turns you on. One of the things that gets very interesting to talk about is decompositions of a graph, where you group together the nodes that aren't neighbors with each other, sometimes referred to as a chromatic decomposition or a coloring of the graph. And it turns out that that process itself is an NP-complete problem. And if you try and do it in a large graph, it will take you a long time. I know, I've tried. And you can sit there looking at your very expensive, powerful Mac Pro, going, why is it getting so warm whilst it's doing that? But the reason why you might want to do that is because it tells you lots about the structure of the graph. And in particular, we're going to get into talking about information theoretic concepts of the entropy of a graph. And of course, everybody who's got a physics background immediately gets a warm and fuzzy feeling because I just said entropy. Okay? So there's lots of other things we can start to break down about graph theory. There are lots of special types of graphs. The most obvious special type of graph is called a perfect graph. And that's a graph where every node is connected to every other node. Okay? And kind of almost, I guess, the opposite of a perfect graph. Well, actually, technically, mathematically, if you're going to be opposite of a perfect graph, it's a graph with no edges. But in terms of network science and what we get excited about at Moogsoft, star graphs are kind of the opposite of it, where one node is the hub for all of the other nodes. And the reason why we think of it as opposite in some senses is a perfect graph or a mesh is very resilient. Like if I cut an edge, everything's one edge. Everything is still connected to everything. Whereas in a star graph, if I cut an edge, something just became disconnected. And back to the Netflix thing, in the network management world, we care a lot about things becoming disconnected. The other thing is clustering. So when we mean clustering in the context of a coefficient of a graph, we get very excited about triangles. Why triangles? Well, triangles is, if you think about a graph of 3 nodes, a perfect graph on 3 nodes is a triangle. Everything is connected to everything. Okay? So, so the number of triangles that you have in an arbitrary graph tells you about how close to perfection you are. And you can measure it by counting the number of triangles divided by the number of open triples. An open triple is an L. Node, 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 no edge there. Okay? we also like to talk about the edges in a one-hop neighborhood. So if you're in the network science world, they use this definition of clustering coefficient. And part of the reason is because it also gives you a probability as to whether any two randomly picked nodes are actually connected to each other. And it gets used as such. And we further abuse this later on. Why? Because it was convenient. That's the other thing about graph theory. There's an awful lot of definitions which really are somewhat arbitrary, but they tend to be useful down the line. Okay? Diameter of a graph can be very useful because it tells you about what the maximum shortest path is across a graph, kind of how many hops from end to end it is. And it sort of can be used also when you start getting into dimensional measures of a graph, which is kind of fun. When you think about what the effective dimension is of a graph, what does that really mean? Get back to you on that later, but in essence, if you were living on that graph and you weren't aware of the rest of the world, you can measure things like how the diameter scales with the number of nodes, or things like probability of return on a random walk, and they're kind of very closely related to dimensional considerations. So diameter is kind of measured in that way. Centrality is even more interesting, and there are loads of different measures of centrality. Centrality tells you about how a given node in a graph, for all of the paths that you could take between any pair of nodes in the graph, how important that node is to the connectivity, how many shortest paths pass through a given node. Back to the we care about things becoming disconnected point of view. Imagine that you were a bad person, and what you wanted to do was bring the London Underground to a halt, or for that matter, the New York subway. Let's not pick on any particular given mass transport system. You would take a map of the subway and you would find the station with the highest betweenness centrality, and you blow it up. So in the London Underground, it turns out that Earl's Court or Piccadilly will do that for you, if you're listening. And so the inverse case of that is if you want to keep the network up, you better make sure that the security is higher at Piccadilly Circus or Earl's Court. So you see how this kind of starts to play. In the fault localization world, that tells us centrality a lot about where we should be looking for problems. So it's super important. Now, the other thing that people of a mathematical mind like to do is, so I'm sure some of you will encounter category theory and all the rest of that kind of stuff, where you discover that this whole body of mathematics is absolutely equivalent to another body of mathematics. It turns out you can represent any graph as a whole series of matrices. Then you have the entire infrastructure of linear algebra at your fingertips to do kinds of fun things. So you can define lots of different matrices that capture the structure of the graph. The most basic one is something called the adjacency matrix. And this is where you kind of put all of your nodes there and all of your nodes there, and you fill in the gaps, zeros along the diagonal. Don't ask me why, but it's handy later. And then you put a 1 where there's a link between each one of the nodes. Okay? It's straightforward. The adjacency matrix is super interesting because if I square the adjacency matrix, the number that I find at the point ij in the matrix tells me the number of paths of length 2 between node I and j. If I cube it, the number of paths of length 3, fourth power, 4, and so on and so on and so forth. So it tells you a lot about the structure. The degree matrix is 0 everywhere apart from on the diagonal. Along the diagonal is the degree of the nodes. Okay? And then you can form this thing called the Laplacian, which is degree minus adjacency. And you're probably at this point going, will you please stop molesting me with making up matrices? Why am I interested in a thing called the Laplacian? And by the way, why are you calling it the Laplacian? Because don't I encounter that in differential equations? Like, what's this got to do with anything? Well, guess what? It turns out that in discrete models, let's say you build your graph out of metal rods and metal spheres, okay? And I wanted to heat one of those spheres up to 100 degrees centigrade. and then compute what the temperature is of the other nodes after a certain time t. If that was a continuous model, I would be using the Laplacian, the heat equation, to solve, and I would get that, and I would get nice little curves, and it would all be cool and all groovy. It turns out that you actually, in the discrete model, use the Laplacian matrix in exactly the same way as you use the Laplacian operator. Which, by the way, if I were given the non-safe talk, remember the safe versus non-safe talk? I just use that to some fun effect in a model of space-time to recover the Schrödinger equation. Because you have Laplacians on graphs, you have nabla squared, it's all kind of cool. So lots of fun. Right, now, it's time we got to putting all of this to work. So I'm going to survey 2 different ways in which we can use graphs to help with fault localization. And at the end of which, I'll make some comments about which ones I really like and which ones I really don't. So I'll start with the one that I really don't like. So I've already let the cat out of the bag. Rules-based approaches. Up until 2010, to kind of take a rough guess as to when we realized there was a different way to do this, this was the entire state of the art for fault localization. Here's what we did. We would build a state model of a network. We would say, here is my map of the network, which I turn into some kind of graph. And if I go and I pour coffee over this catalyst switch from Cisco, apart from ruining a few $1,000s worth of switching equipment, I would get a collection of alerts that would start to come from my monitoring. Because quite often, more often than not, the way in which networks are monitored at the infrastructure layer is you use this thing called ping. Everybody know what ping is? You must ping from time to time. Does anybody know what it stands for? I love this. I mean, it's kind of died in the depths of time. It stands for the Packet Internet Groper. How about that for an acronym? I bet that didn't think of that in those days would be spoken about in hushed tones in 2019. But anyway, so what it does, it goes out and it sends an ICMP packet out across the network. It hops all the way through all the various different sort of segments, gets to the end, and is built into the TCP/IP protocol that it gets echoed back. Okay? So if the thing at the end is alive, you get your ping packet back. You have packet internet groped the end of the connection. Okay? So you do this pinging. You do it from a central point in the network, and some idiot like me goes along and pours coffee on a switch. And what happens is the packet gets all the way to the switch and then doesn't get any further. And so I don't hear the echo packet come back, and I conclude that actually the thing I'm pinging, which is at the distant end of the network, is dead. And I conclude incorrectly, because actually what's happened is it's the switch that's the problem, not the server. This is a use case that is sometimes referred to as downstream suppression. And it's super common, and people suffer from it in the real world the whole time. So some of the things that you do is you can build these rules-based approaches, which you can say, if I've got a ping fail, because remember, I'm pinging everything, not just the thing at the far end. So if I've got a ping fail for this switch, which is now dead and gone to coffee heaven, I'm also going to get a ping fail from everything that's connected to the switch, so I can build this kind of state machine that will show me to ignore, or tell me, inform me to ignore the ping fail from the server at the far end and focus on the ping fail from the now dead switch. Okay? And you turn these things into state graphs, and it's super exciting and doesn't work very well. So the problem is with it is it's incredibly widespread as an approach. So I don't know whether you saw, whether this kind of stuff hits your consciousness. We pay a lot of attention to this. And there was a massive outage at Yahoo Mail recently. We happen to know quite a bit about that outage at Yahoo Mail because we manage the Yahoo Mail network with our software. And it actually turned out that it was an example of they were pinging a bunch of things, and we caught it for them because the system that they used previously was using this downstream suppression, but we sit on top of that and use machine learning to capture the fact that actually it was the DNS server that died, that caused it. But outside of Yahoo, this is used everywhere. Telephone companies, for the large part, are still stuck in this kind of, they use a product called TMEP that uses this approach. And in fact, there's a thing called ITIL, which was built by, it was really the infrastructure library in the UK. It's not a particularly British thing, it's kind of adopted worldwide, but it was kind of built by them to kind of deal with the limitations of systems that aren't capable of being able to do that downstream suppression. So things did get a little bit more sophisticated. We can start to use more of a graph theoretic approach. There's a thing called Codebook Correlation that came about in the kind of the mid-1990s, and Shmuel Kleiger was the inventor of the algorithm. And basically what it does is you kind of look at all the various different matrices of symptoms and problems, and you start to turn it into a causality graph, where you weight the edges by the probability of a given problem causing a different symptom. So my switch gets coffee poured on it. What's the probability that I'm going to get a ping fail from the switch? And so on and so on and so forth. And then when you have that, you can take your set of alerts and compute a similarity measure between your set of alert and which one of the columns in the codebook matrix is most close to it. And it's better. It does a better job than a rules-based approach. But it's still not a particularly good job, because if the network changes, I have to reanalyze all of this down into symptoms and problems. I have to change the code book, and there are all kinds of issues that come about with that. So here's 5 fatal flaws of the rules-based approach. It's not very good at picking up null events. So that's the thing that didn't happen, right? So I didn't get an echo back. It turns out that it's almost impossible to reduce a unique set of potential causes and build a behavioral model that is non-degenerate. So in other words, this set of alerts could have either been caused by my coffee on the switch, or it could have been caused by actually the switch and the server dying. They're two identical possibilities. Order of arrival, you have this issue of if I've got a state machine, state machines have a fixed progression through them more often than not. And so the order of arrival of the alerts is super important. Completeness, can you really predict every possible thing that could happen to your networking system? And then there's this nasty little couple of NP-complete problems buried in there, max, sat, and closure. One of which is about whether or not an arbitrary collection of Boolean logic will ever halt, and the other one to do with the business of being able to understand and decompose your causality graph into discrete and non-degenerate paths through it from a finite state machine perspective. So there has to be better ways of doing this, and the good news is there are always. We have one. So, graph entropy. So the thing I didn't say about betweener centrality is it's a bear to compute on an arbitrary sized graph. I want to say, and I'm pulling this from memory, and I probably should have written it on the slides, that the best known algorithm I think is Brandeis, and it's n cubed roughly. Slightly better than n cubed in terms of the computation of betweener centrality. So graph entropy, we're going to get to seeing how we can do a better job than n cubed, is fundamentally the punchline. So graph entropy measures the structural information in a graph. One way of thinking about it is what's the minimum number of bits that I need to have to encode all of the edges and the nodes in the graph. It was actually first thought of by a scientist in Czechoslovakia called Janusz Kerner. And he was actually thinking about the classic sort of Shannon entropy setup, but with some signals being not distinguishable. And I'm probably going to get this the wrong way around, but let me give it a go. What you do is you compute a graph where the nodes are the symbols, and you draw an edge where the symbols aren't distinguishable. And you have a probability distribution across the symbols which is associated with each of the vertices, and you then write down a sentence of almost incomprehensible pure mathematics talking about convex halls of polytopes of the graph, and it's kind of groovy. It takes about a good solid morning with plenty of coffee to understand what is written in about 50 words. Okay? But it's kind of worth it if you're into that kind of thing. So kernel or structural entropy is this kind of quite abstract measure of the information encoded in the graph. And if you turn the probability distribution into a uniform distribution, you end up with the kind of residual informational entropy of the graph, and we mostly concern ourselves with that. Or at least we mostly, when we get to the application of this, assume that the probability is uniform, which is an assumption. The other one is sometimes referred to as chromatic entropy, which is a much more colourful name. So somebody got the joke. Oh, thank you very much. It's not much of a joke, but there we are. It's not quite as good as a Schrödinger joke to be, and also Schrödinger, or not to be. We'll end there. So the chromatic entropy of the graph, this uses, remember I said you can decompose a graph down into these things called stable sets, or the chromatic sets. These are the color rings. So everybody's familiar with the four-color problem. In fact, the origin of graph theory was the Koenigsberg bridge problem, where it was eventually proven that you couldn't take a path around the island in Koenigsberg without crossing one of the bridges more than once. And this was done by thinking about representing that as a graph and thinking about the colorings of the graph, how many colors you could use to do that. So chromatic entropy, literally what you do is you decompose a graph down into its sets of non-adjacent vertices, and then you do some probability measures on top of that. What's interesting, and just these are a lot more simple than the graphs and smaller than the graphs that we deal with on a sort of a day-to-day basis, but here's some kind of prototypical graphs that you see in network science and in network management. So the star graph on 4 nodes, S4, perfect graph on 4 nodes, K4, the cycle on 4 nodes, C4, and the path, which is an on-closed cycle on 4 nodes, P4. And if you look at what maximizes and minimizes chromatic and structural entropy, you can see why people sometimes refer to chromatic entropy as neg entropy or negative entropy. But what's kind of interesting here is, remember back right at the beginning I said we get all kinds of excited about star graphs and perfect graphs in the network management world because star graphs I chop on link and I get something disconnected. Perfect graphs I chop on link and nothing happens. Okay? Now I've got a metric that I can compute that tells me when a graph is perfect and therefore resilient, or when a graph is not perfect, more star-like, and therefore not resilient. So now I'm kind of, this is cool, right? Bugger, right, which is a wonderful English phrase. It turns out that it doesn't tell you anything about the individual nodes. It's computed across the whole of the graph, and also, in both cases of the global definitions, it's a bit of an NP-complete problem in of its own right. So we are now dead in the water. Except one of the great things about science is, nobody really tells you not to break the rules. So you can break the rules. What we really want is we need a value which we can compute easily for a vertex, a single node in the graph, that if you sum it all up, you end up with something like the whole of the graph entropy. And if I can convince myself that it does that in a way that is well behaved, so in other words, you end up with, if you double the complexity of a graph and double the entropy, the vertex sum also kind of more or less doubles, so it follows the same sort of dependencies. Then we're back in business, and we can do something useful with those computations. Now, it turns out that there's a guy called Matthias Damer and Abi Mushevitz, great names, and they started thinking about this kind of functional decomposition of a graph and how that might relate to entropy. And what they said was, well, all you really need for an entropy measure in the kind of the Shannon sense is a probability distribution across some sort of alphabet, and why not just associate the alphabet with the nodes of the graph? And providing that you can produce a well-defined probability measure, that's fairly straightforward to do, then you can go ahead and you can compute your entropy for a vertex, and you can sum all of that up and you get your graph entropy. Now, what he talked about was functionals or functions on a vertex. And so you start to ask yourself about what can you know about a vertex. So Matthias added in an additional concept of these hop neighborhoods of a vertex. So if you start at a given node and you say, give me all of the nodes that are one hop away from this node, and you get this kind of thing called a J shell, a one shell. Then you can say, what about at 2 hops, and you end up with another shell. And of course, this is constrained by the diameter of the graph. Now, we liked that approach, but here's what we didn't like, is it offends my sense of kind of progressive sort of continuity, so what happens in the continuum with the graph. So we started to think about, instead of the nodes on the shell, the subgraph decomposition at hops from a given vertex. Okay. And what we did is we said, well, okay, these are pretty naive calculations, but what we can know about a vertex is we can know its degree. Okay, so we'll create a functional which is the inverse of the degree, and we'll create another functional which is the degree over twice the number of edges. The reason why it's twice the number of edges is if you sum the degrees up, you get twice the number of edges. Okay? And you can construct an entropy out of that. Right, so off we went. That's fantastic, we thought. It's really cool, and we did some experiments. I'll get to the results of that in a second. However, the trouble is with that is not all high-degree nodes are, in some sense, more important than others. It kind of depends upon how they're wired into the rest of the graph. So clustering has an important consequence there as well. So we then took the clustering coefficient, and what we did with that is we sort of slightly abused it, because the clustering coefficient of a star graph is 0. And if what we want to do is we want to penalize high clustering graphs, when you divide anything by 0, you have an unfortunate infinity, and that would be a bit of an issue. So what we did is we included the central node in the definition of the clustering coefficient. So with a star graph, you don't get 0. And then we performed 2 more functionals on the vertex, which is the same as what we did previously, but divided by the local clustering coefficient. Okay? And came up with some more lovely formulas for this. Now, when you sum this across the prototypical graphs, because you can analytically work this out, it turns out you end up again with this business of being able to pick out the difference between a very perfectly meshed graph and also a star graph or a cycle graph in this particular instance. And we did lots and lots of work. There's an IEEE paper, full TNSM paper, which kind of goes into the gory detail, which got us comfortable that it is all the various different desiderata of Shannon for an entropy, so subadditivity and closure and all the rest of that kind of fun stuff. So, kind of to the punchline. The first thing, second thing, third thing, in fact, that we did was we went and checked, because we got so excited about it, we actually applied it to real-world event data. I'll get into that in a second. But what we did later on was we looked at how this compares to actual computed values for structural and chromatic entropy in certain types of randomly generated graphs. We chose Barabasi-Albert preferential attachment graphs because there's a kind of a belief that there is some relationship between that and real-world networks. I'm creating a lot of static. That might be me. And also we did Erdos-Renyi pure random graphs. A pure random graph being, you can do it one of 2 ways. You either fix the number of nodes and have a probability of an edge between any 2 nodes, or you can do it where you have a probability of connecting a node into the rest of the network. And what we found was there was a curious correlation between vertex entropy summed over the whole network and real entropies for these kind of random graphs. Now, I want to stress here that this is not a general result. There is no belief or confidence that the 2 are equivalent across generic graphs. Okay? No belief. But the fact that there is a correlation with randomly generated graphs kind of got us comfortable that there's some content in what we're doing here, because again, back to it, randomly generated graphs do share a lot of macro properties with real-world networks. So, Yahoo. So we have a very nice relationship with Yahoo, and they allow us access to a lot of data. And in particular, what we have is we've got the full topology of their network. So we can compute vertex entropies across all of their network. We also collect the number of events and the number of incidents on their network. So what we can do is you can produce these cumulative distribution graphs of events by vertex entropy and incidents by vertex entropy. Now, an incident is an event that's caused a problem. So these are the things that you want to catch. An event that doesn't cause a problem is noise. So one of the things that you want to do in a real-world network management situation is you want to throw away noise and keep the good stuff. Okay? So what you can see with these cumulative distributions is there's a rather delightful gap between the distribution for events, the thick line, and the distribution for events. So you can throw, literally, if I draw a line here, I would throw away 60% of the events and retain most of the incidents. And we do this with most of our customers now. We've taken vertex entropy and turned it into an interaction. We even did some rock plots. And actually, this again was under some duress, because people said to me, produce a rock plot for vertex entropy. And I said, what, are you crazy? It's not a classifier. How can we produce a rock plot? It wouldn't make any sense. But OK, then, we went and produced a rock plot. And what we found was, it's not great. Let's be honest. Okay, it's not the kind of the sort of the nice angular graph top left. But by gosh, it's kind of on its way to being a classifier. It's actually pretty good. So if all you want to use it for is a bandpass filter to remove noise and retain the signal, in fact, you get a lot further than that, generally speaking. Okay. So vertex entropy turned out to be, for us, the takeaways are a great way to eliminate noise for fault localization. And it also turns out to be nearly good enough as a way to construct instance out of the underlying network. So we're very pleased with that. By the way, in other work, we've used vertex entropy to do lots of other things, including a competing model to preferential attachment that builds networks on a max entropy basis and produces a degree distribution, for example, that is far closer to real-world degree distributions than the 1 over k cubed that you get from preferential attachment. We're nearly there. What I left out? Well, everything really. There's lots and lots and lots of other things that we could do that use graphs in fault localization. So neural net effectively is a graph. We use neural nets quite a lot. You can analyze neural networks using graphs. You can analyze neural networks using vertex entropy if you so desire. In fact, one of the projects that we are working on at the moment is can you use vertex entropy as a way of informing the solving algorithms of a neural net, so you don't spend a lot of time adjusting the weights on nodes that are slow moving. We developed a lovely time correlation algorithm using convolution to create a time similarity graph, matrix actually, for events. And then we turn that into a graph, and we use modularity decomposition that picks out clusters of co-occurring events rather nicely. And then there's all kinds of other fun stuff with fault propagation things and Bayesian networks. There's a ton of applications in the fault localization space. So, conclusions. It's cool. We like graphs. They are incredibly useful things to use in a very real-world application. For my money, an awful lot of time is spent running around chasing deep learning and all the rest of it, and you can actually get a long way with a good, healthy dose of graph theory and network science that's in there. The structure of a graph, obviously, is super important to our world where we're doing fault localization. And there is a huge body of work in graph theory and information science that you can leverage. I'm sure most people in this room have heard of Paul Erdos, right? There are probably some people in this room who even track the Erdos number. How close you are to having published with somebody who published with Paul Erdos. Most of the body of Paul Erdos's work was combinatorial mathematics and graph theory. And I mention that just to suggest that somewhere lying around in the publications will be techniques that you can lift off the shelf and make beautiful music with your real-world data science application. So to me, all of this underpins this unreasonable effectiveness. They're just so handy and so useful. It is surprising that they're not more used in the commercial systems and network management space. So a couple of things. I want to thank everybody who looks after me. Loads of fantastic collaborators across many different institutions. And then, of course, there is my super wife who helps by being the person who listens to me and lets me talk about all kinds of weird things and then points out where I'm being stupid. So thank you very much for listening. And be delighted to take questions.
Let's take our speaker first. I think that mic is dying, so I was gonna give this to you.
Okay, right. Okay, I'm not sure whether that's. Oh, okay. I can hear myself.
Is there any questions for our speaker?
Yeah.
It's kind of a two-parter. First of all, you mentioned the book by Gervasi. What's that book called?
So he wrote this book called Network Science, which is fairly recent. I mean, there is actually a paper which you can go and find on, it's fairly easy to find, called The Statistical Mechanics of Complex Networks. It's famously the most cited academic paper ever. So it's incredible. And it's a very comprehensive review of all of network science. The book is kind of like the glossy hardcover, lots of really cool graphics, and a very nice section at the beginning where he describes exactly why he's so famous. So if you can skip that bit, you just get to the good stuff.
Sorry to take up time for questions, but the second question I had is, I can see how network or like graph theory could be actively applied to like some instances of natural language processing,
Mm-hmm.
named entity recognition. I was
Yeah.
wondering if you've done any work around that.
So funnily enough, actually David and I were talking in his office before the talk, and we're just beginning to look at applications of both discrete graph theory, topological data analysis for that. So Gunnar Carlson over at Berkeley, I want to say, or is he at Stanford, kind of wrote the book on it, and there's loads of really interesting stuff there where you turn data points into a graph in embedded space. And they use some algebraic topology to make statements about how similar a set is to another reference set. You can also do some really interesting things in the continuum limit with the sort of algebraic geometry of these things, which we're starting to look at as well. But there is a ton of application in NLP and semantic analysis and language analysis that you could really go to town with. Open field. Cool. Every time I move, I crackle. Is
There
that
we
one?
go.
Okay,
There we go.
fantastic.
So I was just going to comment on the fact you use vertex entropy, and there's lots of other types of node-based statistics you can use. There's also a huge now push towards doing automatic feature selection. Right?
Yeah.
So thinking about embedding and things along these lines. Have you done any kind of comparisons between these types of methods? I mean, it's always kind of interesting to be like, what's the handpicked, motivated by graph theory type ideas where the machine learning come up with their embedding and see what they give you.
So no, we haven't, and not lost on me is the even just inside of the entropy definition, you define a feature on the node, and of course if you're not talking about just a kind of a plain boring graph, but you've got more feature, you could do all kinds of other interesting stuff on it as well. It's a very, very, very open topic, and one of the really cool things about it is The rules are still being written, so it's one to have at.
In regards to your work experience, were there any particular findings that you would say were only exposed after applying graph theory to it, or any of those particularly notable?
So yes. So one of the other research projects that we're involved in, it's actually our PhD student at Sussex, is actually inferring functional topology using events to go in the other direction. So I see event on node A and followed by event on node B shortly afterwards, so I can infer a link between them. And one of the things that we discovered on a large cloud provider's network between two zones that are supposedly independent is that they're not. Yeah. So, by the way, if you ever wondered why Amazon goes down a lot, now you know. Yeah. Yes.
But then you applied it to, say, Yahoo's network.
Yeah.
Did you see that in practice a lot of these like commercial networks are fairly similar to the graphs?
Yeah, so and a bit more color on that, because it sort of seems like that might be surprising, but then it turns out that it's kind of not, because people do simple things repeatedly to construct a graph, and that tends to mean that you're building the graph actually from simplices, and simplices tend to have a very straightforward structure to them, and they tend to have the same sort of structure actually as a Barabasi-Albert preferential attachment graph. But we puzzled a lot about this. What we found with most of the real-world network graphs is they tend to either fall into a kind of what's sometimes called a forest. So basically lots of star networks assembled into a tree with a centrally meshed piece, or they're just a full-blown mesh, which we sometimes refer to as a fuzzball. And typically you go between the two. The fuzzball is not very much like a preferential attachment graph, but has also very trivial characteristics. But the forest, the kind of stuff you tend to see, actually does look very much like a PA graph. And in fact, one of the when you go read that book or pull that paper, one of the things that was kind of like an early win for preferential attachment was they applied it to the autonomous systems graph in the early internet, and came out with this very short Nature paper talking about the resilience and vulnerability of the internet. And it's precisely because it mirrors very closely a PA network.
So you mentioned that some work with like biological systems and cancer and whatnot. Is there any sort of relation in like the graphs you work with these big software companies and what the work you've done with the biological systems?
Wow. So that is a really, really interesting question. So there's a researcher, a great researcher down at ASU called Sarah Walker, and she spends a lot of time trying to understand the difference between biological networks and non-biological networks. Is there something characteristic about a network of life? So a gene regulatory network, or an evolutionary competition network, anything that is kind of characteristic of life. And to date, we've not really got our hands around it. We can sort of see that there are differences. I would say that typically the networks that you see in, say, gene regulatory networks tend to be much more perfect, so much more resilient. I mean, this is a difficult topic to talk about because it touches a lot of people. But the progress of cancer is very unfortunate because you typically cure one cancer and die of another. And so there seems to be like a resilience in how the genetic sort of background to the emergence of tumors survives treatment. And there's thousands of people trying to research how to fix that, of course. But I get interested in the spatial networks of cancer. So there are lots of people focused on things like gene regulatory networks and the somatic mutation theory of how tumors arise. There's more recent work, actually mostly done at UCSF, around symbiosis between cells. So the idea that it's not just about one cell going bad, but actually the genetic degradation of your tissue, which is going on right now, as we're sat here being bathed by cosmic particles and drinking coffee and doing all the fun stuff that kind of kills you. That of course, you're all young, so you're not going to be at the stage where you've got prototumors But you may have two cells that are degraded enough that they can cooperate to cause a tumor. And that's something which I'm active in. Cool.
We actually are out of time. Phil actually has to run out, but we'll be able to have a little bit of the usual scrum for about 10, 15 minutes. But let's thank Phil one more time.
Thank you.